Speaker is Dr. Linda Sharp. She is an epidemiologist in Irish Cancer Registry. Her title is Association Between Population Density and Cancer Risk.
Okay. Good afternoon, and thank you very much. And I'm going to talk about a study we did in Ireland about associations between population density and cancer risk. So as we heard from David Foreman this morning, studies of the geographical variations in cancer have a long and distinguished history, and they're important because they can provide us with clues about disease etiology. And this is not only true of studies of geographical variations between countries, but it could also be true of studies of geographical variations within countries. For example, the area we're interested in is urban-rural variations within individual countries, and there have been some studies which suggest that the incidence of particular cancers might vary between urban and rural areas within countries. But the question we had was whether these associations simply reflect socioeconomic differences between urban and rural areas. So what we set out to do was undertake a systematic investigation of urban and rural variations in cancer incidence on the island of Ireland, adjusting for socioeconomic status. So our data sources were the two population-based cancer registries on this island, the Northern Ireland Cancer Registry, which covers a population of 1.5 million and is based in Belfast, and the National Cancer Registry, which is here in Cork, and it covers a population of 4 million, so the yellow part of the island. And what we did is we extracted data on invasive cancers from the databases of both registries, and we did it for the years 1995 to 2007. And we looked at 18 cancer sites or groups of sites, so the 18 most common groups of sites ranging from head and neck cancer through the gastrointestinal cancers, skin cancer, genitourinary cancers, brain and CNS, lymphomas and leukemias. And what we needed to do was to get an urban-rural classification that was comparable in the two different countries. So what we had to do was to create a classification based on population density. So we assigned each cancer case to the smallest geographical unit for which population data are available based on their address at diagnosis. And we created three categories of population density. These included approximately 1/3 of the population. So areas that we've called rural had less than 1 person per hectare, and is about 36% of the population. Then we've got intermediate areas, 1 to 15 people per hectare, and then we have urban areas, which is more than 15 people per hectare. We then calculated relative risks for each cancer site, for intermediate and for urban areas, each of those versus rural areas, and we use negative binomial regression for that because it allows for over-dispersion of the data. We adjusted our relative risks for age and for country, so Northern Ireland or Republic of Ireland, and also for socioeconomic indicators. Now, what we needed, again, were socioeconomic indicators that were available in the two countries. So we had to derive these from census data in the two different countries, and we could come up with three comparable indicators. Percentage of people unemployed in the area, the percentage of people in each area who didn't have a degree from college or university, and the percentage of elderly people in each area living alone. And when I show you the results for the cancer sites, I display them in three groups according to whether or not the cancers were associated with these measures of socioeconomic status. So first of all, I just want to show you how our measures of population density play out when you look at them on a map. So the blue areas here are the areas, the urban areas, so more than 15 people per hectare. And that's really the centres of the cities. So you're talking about Cork here, Limerick, Galway, Derry, Belfast, and Dublin. And then our intermediate areas, so that's 1 to 15 people per hectare, are typically the periphery of the cities. You can see that around Dublin here, exploded out, and around Belfast, even around Cork and the other cities, and then odd towns across the country. And then the rural areas, less than 1 person per hectare, are all these green parts of the country. And although that's most of the land mass, it's only 1/3 of the population. I'm going to show you now why it was important to adjust for socioeconomic indicators. So we created measures of unemployment. So we created we grouped areas according to level of unemployment, and we created 5 groups. And each group had 1/5 of the population in it when you looked across the entire island. So by definition, if you look at the highest unemployment areas, 1/5 of the population fell in there across the entire island. But if you look just at the urban areas, 30% of the population falls in the areas with highest unemployment. In the rural areas, by contrast, only 13% of the population is in the areas with highest unemployment. So because urban areas have higher percentage of unemployment than rural areas, we adjusted all of our results for urban-rural status, for unemployment, for percentage of the population without a degree, and for percentage of elderly living alone. So these are the first results for the urban-rural status and cancer risk, and I've shown it for 4 cancers that are associated with higher socioeconomic status: non-melanoma skin cancer, melanoma, breast and prostate cancer. So these are our relative risks. The grey bars are for intermediate areas, and the blue bars for urban areas versus the rural areas. So everything on this side of the graphs means higher risk in the intermediate or urban areas, and on this side means lower risk in the intermediate and urban areas. So you can see for 2 of these cancers, non-melanoma skin cancer and breast cancer, there was higher risk in intermediate and urban areas, and those results were significant. For melanoma, there wasn't much of an association. And for prostate cancer, the risk was lower in the urban areas than in the rural areas, and that was significantly so. Now I'm going to look at our 7 cancers that were associated with lower socioeconomic status: head and neck, esophagus, stomach, pancreas, lung, bladder, and cervix. Okay, so out of these, 6 of them were actually associated with urban residents. So for 3, head and neck cancer, for lung cancer here, and for cervical cancer, the risk was 50% higher in the urban areas than in the rural areas. For 3 others, esophagus, stomach, and bladder cancer, risk was 20 to 30% higher in the urban areas than the rural areas. And remember, these are adjusted for socioeconomic status. And finally, for pancreatic cancer, there was no association between urban-rural status and risk of pancreatic cancer. So for our final 7 cancer sites, these are cancers that weren't strongly associated with socioeconomic status. We've got 3 cancers at the top: colorectal, kidney, and brain cancer. We had very modest associations with urban residents, about a 10 to 15 increase in risk in males for colorectal cancer, females for kidney cancer, females for brain and CNS. For ovary, uterus, NHL, and leukemia, there was no association with urban-rural status. So what we found when we looked at these 18 cancer sites was 11 of them risk was consistently higher in urban than rural areas. So what are the possible explanations? Well, the first thing we need to consider is that this may well just be an artefact. So is it an artefact due to registration processes? Well, that seems unlikely because both of the registries work hard to identify cases that are diagnosed in small hospitals out of the main population centres. The next option is whether it's due to an ecological fallacy. Well, if it is, then the most likely thing it would be is some measure of socioeconomic status, and we've adjusted for that, so that also seems unlikely. It's also possible that it could be due to some kind of residual confounding from our measures of socioeconomic status. That seems probable. If we look at our urban areas in Ireland, both the most affluent and the most deprived areas are contained within those urban centres. And it's probable that our measures of socioeconomic status really don't capture that perfectly. But what we think is also probable for some cancers is that there may well be urban-rural variations in access to screening and diagnostic services. That seems likely for cervix, breast, possibly for non-melanoma skin cancer. And then for the other cancers, well, there may well be urban-rural variations in risk factors. And this is where we just don't have data. But it seems to us that what these findings are pointing to is urban-rural variations in smoking prevalence. These types of variations may also be there for HPV, for cervical cancer, maybe for UV exposure, for non-melanoma skin cancer, for occupational exposures, for bladder and other cancers, and maybe for some other risk factors. So in conclusion, we found striking urban-rural variations in the incidence of 12 out of 18 cancers in Ireland. 11 of those cancers were significantly associated with higher population density. The associations were evident after adjusting for socioeconomic indicators, and we think these associations are intriguing and they should be further investigated, particularly for those cancers whose etiology is not well understood. Thank you.
Thank you very much. It's a very attractive studies focusing on population density on cancer risk.
Yeah. Linda, thank you. Yes, thank you. Exercising chairman's right here by asking questions, the droit de seigneur. So let me just ask you a question. Very interesting study. What about the people who had been living in the country and then moved into the higher population areas? Did they differ from the country incidence? I'm just thinking of, for example, prostate cancer in Japan, and then tracing it to the Western United States, where the incidence changes completely. So,
yeah, I mean, absolutely. The issue of migrants could be important here, and particularly, I think, in the Republic of Ireland, where there's been big kind of demographic changes over the past 20 years with the Celtic Tiger. But unfortunately, we only have information on their address at the time of diagnosis with cancer, so we don't know where they lived before that. But it's possible that that might be driving some of what's going on, and perhaps particularly, as you say, for prostate cancer.
It might be an interesting study.
Yeah.
Any other questions? Oh, please.
Thank you very much. Did you adjust or look for the stage distribution among the different regions of residence?
We didn't look at whether there were differences in the stage distribution, because this work was just solely focused on data that we had that was entirely comparable for all years between the two registries. And the Northern Ireland Cancer Registry has detailed stage information for particular years. But it's something that we could go on and look at and see whether there are differences in stage, and perhaps even whether there are differences in patterns of treatment received.
Any other questions? No? Oh, that's.
Thanks, Linda. Just inquiring, were there any differences between the north of Ireland and the south of Ireland?
There were. I mean, we did adjust for country, because there were, when you looked across the cancer sites, there were some systematic differences between the countries, and for quite a number of the cancer sites, there were. The incidence was higher in the Republic of Ireland. The most notable one was prostate cancer, where we have much higher incidence here than in Northern Ireland, and it's due to widespread PSA testing. And for some of the other cancers where there's screening in place, there were differences in incidence, but in this analysis, we adjusted for those, so that's not what's driving this.
So, thank you very much.
Thank you, Linda. So we'll move on to our next speaker. Thank you. Next speaker is going to be Tina Jagar from Ljubljana. And she is from the Epidemiology and Cancer Registry, the Institute of Oncology in Ljubljana. And we're going to hear about Slovenian maps of local standardized incidence ratio.
Hello to everybody. So to start with, we have reasonably believed that the data from Slovenian Cancer Registry are of sufficient quality to make some geographical epidemiology out of it. We have available the geographical coordinates. Oh, I'm sorry.
Okay.
Should I start again?
No, no.
No, okay. So we have this coordinate data for each cancer case as well as for population data, which is about roughly 2 million inhabitants. Our question was, can we produce a map of Slovenian cancer map based on point data instead of aggregated data? We developed a procedure and named it local estimation of SIR, standardized incidence ratio. We collected female cancer patients with cervical cancer on a 6-year period, and this makes about 16.7 per 100,000. This is average annual crude incidence rate. From Central Population Registered, we obtained for all Slovenian population, for every person, data on personal identification number. We used it for linking the two data sets. We obtained the exact coordinates of the place of permanent residence, and of course gender and age data. We need this for calculating standardized incidence ratio. We wanted to compare several types of maps based on the same underlying data set. So we needed first to aggregate our point data to some administrative level. This is a map of standardized incidence ratio by municipalities. Of course, municipalities in Slovenia are very small areas. Here are typical small regions where one case can move one municipality from low-risk area to very high-risk area. So what can we do about this? We could mask the special areas with small population, but then we would have many white spaces in Slovenia. Nice solution is making a cartogram. These are our two areas with small population. So cartogram is a projection where the size of municipality does not reflect exact administrative border, but rather the population that lives in that municipality. Of course, we could aggregate to larger spatial units, but this is not what we wanted to do. And we could extend the time period, but we already have a 6-year time period, and there is smoothing. This is a map produced using Bayesian hierarchical modeling. We can see a broad spatial pattern with lower cancer risk of cervical cancer in the west, and there is a vertical band in the middle of toward the east of the country. And quite similar spatial trend is produced by method developed by Eero Pukkola and Tommi Patama from Finland. A similar trend is seen, and important for this interpolation is that the two major cities are extracted and plotted spatially, so they does not contribute to the smoothing procedure of the background municipalities. So we have these coordinates. They are plotted in upper corner. This is data confidentiality is secured here because we moved every dot for random direction, for random distance, so one cannot identify the cases. We covered the whole study area with 1 kilometer grid, producing 20,1614 grid points, and we used each grid point as the center of circular moving window. So we constructed a window, a circle, and counted how many population we have inside it, how many cases, and computed standardized incidence ratio for each grid point, and then plotted it on the map. But before I show you a map, this is another important feature of the procedure. The circle radius is not fixed in advance, but is changing from 1 kilometer to 15 kilometer with step of 1 kilometer until predetermined minimum population of 7,000 is reached. This is for cervical cancer. For breast cancer, we used the minimum population of 5,000 because it is much more common cancer site. So, why we did this? because this is how the local SIR estimates are based on approximately the same population sizes, which makes them more stable and more comparable. This is the map with some white spaces, which reflects the circles that in 15-kilometer radius did not reach the required population sizes. And just for comparison, I plotted the map of municipalities over it, and we can see that some SIR patterns reflects the borders of municipalities, and mostly they are not. Is the mouse here? Oh, it's working. So here, this is a coastal region, and here, where my point is, there is the 4th largest city of Koper, where the port is to the sea, and the municipality is very big. The Koper is inside, and a huge rural area with sparse population. So this is quite distinguished on this map and not on previous maps. So how can I know this pattern of SIRs is some true pattern? I don't, of course, as I don't for any other maps I could produce. But what I did is I choose different parameters, and this is much more smoother map of local estimated SIRs, and I can reasonably say that approximately the same spatial pattern could be observed from these all 3 maps, about similar. And these are the same set of maps on breast cancer incidence data for females in Slovenia from 2002 to 2004. Again, this is municipality of Koper on different maps. Disadvantages of these procedures are, of course, that data availability. There are no, point data are usually not available for cancer registries for routine analysis, and data should be of good quality for such an exercise. We still have to decide what to do near the area border and other sparsely populated data, as in high mountain area. And producing a map of locally estimated standardized incidence ratio is quite laborious, but in my opinion as well Bayesian modeling is. So what are the advantages? Map of local standardized incidence ratio estimates is quite a high resolution map with huge emphasis on local patterns, sometimes too many, so one must be very careful how much smoothing is implemented. And the good thing that the local SIR estimates are based on approximately the same population size, which makes them more stable and more comparable. And of course, in this procedure, nowhere we used for cancer mapping arbitrary administrative units. This is just a little advertisement for our interactive web portal, Slora. When one can prepare its own data, you choose parameters and obtain different maps, plots, time trends, and so on. Thank you for your attention.
Any questions from the audience? As a clinician, I'm desperately hoping there are going to be some questions, as I might struggle asking one on this. So thanks for your help, audience. Oh yes, there we go. Yes, thank you very much.
I'm so impressed with your confidentiality protection. Is it really possible to identify an individual from a dot on a map?
No, but I would be afraid if I really plotted the dot where it should be, that somebody would object.
Okay. Just tell them it's ridiculously over the top.
I agree.
Is there much immigration from other countries in Eastern Europe into Slovenia? Slovenia, we always get the impression of a country that joined the European Union and the Euro, and everything happened very, very quickly without any particular problems at all. So one gets the impression of a country that is at peace with itself, and I just wonder if there is immigration there, which might have an effect on your beautiful maps.
That's true. Well, the cancer registry should register all cancers for persons that have permanent residence in Slovenia. Usually, these are workers coming for part-time, not having permanent residence. And that they are all excluded because we have that data. Who is supposed to be in and not. But if, yes, of course, there are some.
Yeah. Okay, thank you. Any other final questions? Well, Tina, I think that's very interesting and impressive. Thank you very much. Fantastic piece of work. Thank you very much indeed. So we'll ask Nicola Botwell to come to the podium. She is from the Southwest Public Health Observatory in the United Kingdom, having spent a lot of time in London, and has moved down there to look at indoor and outdoor work and socioeconomic status and skin cancer, with some interesting findings.
You can use the left and right button on that.
Oh, right. Okay.
Or you can use the...
Thank you. I'm so pleased to have been invited to speak here today in this wonderful part of the world. I'll be presenting results from an exploratory study looking at UV exposure in the occupational setting and skin cancer. I work at the Southwest Public Health Observatory, based in Bristol in England. And we have responsibility for the registration and intelligence of all cancers in the Southwest. We also have a national responsibility for providing intelligence on skin cancers, urological cancers, and end-of-life care. So where is the Southwest in our geographical boundary? We're the blue blob, as you can see on this map here in the left of the country. A little bit about the Southwest. We're a mixture of urban and rural areas. We have some of the highest UV levels in England, of course non-comparable to countries like Australia and New Zealand, but the highest in England. And we also have some of the highest incidence rates in our local authorities in the Southwest. So if we start with a bit of background on skin cancer, as Joanne pointed out, England still has rising rates for melanoma. Indeed, in the Southwest, we still are observing rising incidence rates for our non-melanomas and melanomas. As you can see, the non-melanoma reporting rates are higher, and these are just the tip of the iceberg, because not all non-melanomas are registered in England. But it's important to note that mortality is highest for melanomas. When looking at age and the difference with non-melanomas and melanoma skin cancer, we can see that BCCs start rising more commonly in 50s and upwards, and squamous later again, whereas melanomas are observed at a lower rate. They do rise, but we do observe more at a younger age. So as is common practice, before we started this study, we undertook a literature review. And looking at the literature, to summarise very quickly for this meeting today, the earlier work pointed towards an increased risk of melanoma with greater outdoor exposure. And that's work that was undertaken in the 50s, 60s and 70s. Then more recent research, and it isn't actually that recent, in the 80s, indicated a greater risk of melanoma among higher social class and also, in particular, indoor workers. So we wanted to replicate some of this work and see if we had observed similar findings in the southwest. So where did we turn to for the data? Well, unfortunately, in England, we don't hold information on occupational status in our cancer registration data set. So we had to look to our death registration data. And we extracted all those who had died of a skin cancer between 2001 and 2010. That's C43 melanoma and C44 non-melanomas. And we also extracted, importantly for this study, occupational status. And as you can imagine, there were hundreds and hundreds and hundreds of written occupational status, because it's a self-reported certificate that we had to then classify. So how did we classify our respondents into their UV occupational status? Well, we turned to a model that was developed in 1984 in New Zealand by Cook and colleagues, where they grouped their occupational status into three main groups. So indoor workers, self-explanatory, those people who work primarily indoors. Outdoor workers, again, the same, whereas intermittent workers had a combination of indoor work and outdoor exposure. And you can see some examples in this chart here. So clerical workers, managerial for indoor workers, to horticultural workers, postmen, outdoor, and intermittent workers, architects, surveyors. So what did our sample look like? Well, for that time period, we extracted 3,096 cases, the majority of which were indoor workers, 1,764, outdoor 504, and mixed. I'll refer to mixed for intermittent throughout the rest of the presentation, 305. What did that look like in terms of the type of skin cancer people have died of in the southwest? Well, as you would expect, the majority were from melanoma, then squamous and basal. If we start looking more closely at occupational exposure and skin cancer, here looking at gender differences in occupational status, you can see that for women, the majority or women were more likely to be housewives or indoor workers, whereas when we turn to the outdoor and the mixed intermittent professions, we see more males. And when we look at the type of skin cancer that people have died of, you can see as the age rises, so when we move into the 50s and to the 70s, you can see more people dying of squamous skin cancer. And then you can see basal, people dying with basal skin cancer from the 70s upwards. If we look at UV occupational status by age, you can see that in the younger groups, where we can see with the lines, the red and the green, more indoor and mixed occupations die in younger as an observation. And then when we move to the older age groups, we see a rise in the outdoor and housewife groups. So, if we look at the type of skin cancer by UV occupational status, we can see when we look very closely at indoor, outdoor and mixed, that indoor workers are more likely to die of a melanoma, and that was statistically significant. So that's 80.5% had died of a melanoma. And when you look at melanoma, the percentage dying of a melanoma in the outdoor group, that drops to 72.6%, whereas outdoor workers, non-melanomas, it's 27.4% and 19.5% for indoor. And likewise with age, indoor workers are more likely to die younger, and outdoor workers older. Now, excuse this graph, I don't know how clearly you can see it at the back, but we find this quite fascinating when you look more closely at the professions that are making up those groups. So if we look to this side, on the right-hand side, where you see the non-melanomas, you can see quite clearly the classification of groups that have fallen in here. So security guards, people working in sports, building professions, postal and agricultural workers, where we see the bulge in the non-melanomas. Then when we look to the left, we see IT professionals, teaching professionals, medicine, and managers and directors, and notably hair and beauty, where we see higher socioeconomic status and more indoor work. And we need to do some more work classifying these groups and looking at it more closely. And this shows the power of the data here. So if you see on the horizontal axis the percentage of melanoma deaths, and on the vertical axis the percentage of non-melanoma deaths, you can see, and this is statistically significant, the unskilled outside in agriculture are more likely to die of a non-melanoma, and then the managerial, medicine and professional more likely to die of a melanoma. And we found no significance for outdoor professional groups. So what can we conclude from these preliminary findings? Well, there appears to be different induction mechanisms for melanoma and non-melanoma. Outdoor workers are more likely to die with a non-melanoma, and indoor workers a melanoma, especially those from higher socioeconomic groups. The study highlights the need for perhaps repackaging and phrasing how we present prevention messages within occupational group settings. I'd like to thank you all again, and in particular thank my colleagues from the South West Public Health Observatory who helped with this piece of work, Matthew Arles, Veronique Poirier and Julia Verne. And also show we have a skin cancer hub at the observatory where you can find lots of really useful information on skin cancer, both from the prevention side and also epidemiological data as well. Thank you.
Thank you, Nicola. Any questions? Yes, question here in the front and question at the back. Can we come to the front first? There was the first hand that caught my eye, and then back to you.
Thank you for a nice presentation, and I guess you were not surprised by your results. But there was one thing that surprised me, and you need to tell me how many BCC, basal cell carcinoma patients, did you have that actually died with that diagnosis?
Yes, I'd have to flick back because I haven't got it in front of me. It's a relatively small number.
Yes, it's a small number because you shouldn't die from that disease at all. The question is, have you studied these cases where these sites were situated?
We looked at that. First of all, I should spell out again, I perhaps didn't make it clear at the front end of the presentation. These are people who died of or with a skin cancer. It could have been a contributory factor.
Thank you,
in
that explains it.
So that might help explain that. We did look at site, and unfortunately, within death registration data, it's not routinely collected on site. In fact, squamous was one of the ones where it was best collected, and we really did want to look at that. That was, yes, it'd be useful.
Next one.
Yes, I would recommend to go to the standard epidemiological analysis with this, which is based on incidence or mortality rates and not on proportions. And also then in that way, it would be possible to control for age and so on, because it can well be that some of the workers are older than the others, and because the risk is different in different age groups of these skin diseases. Therefore you will just get something that is very badly confounded. So I think that either you go to the school bench to learn the epidemiology, or try to get from somewhere the way that these studies should be analyzed.
Comment?
It's useful, and we'll take that on board.
Okay.
I couldn't quite hear it all.
So when people in these islands, when we talk in these islands about temperature differences, the people in continental Europe laugh at us considerably because they can only see rain and cloud. However, there is definitely a temperature difference between the southwest of England and, say, Wester Ross, or even Glasgow. Have people in Glasgow looked, or in the Scottish Cancer Registry, looked at similar patients to see if there's any difference at all where there would be much less sunlight?
That's an excellent point, and they haven't that I'm aware of. And the problem with doing this, it's quite an extensive piece of work because of the necessity to reclassify all these occupations. It'd be good to set up perhaps a research project in the future to look at that. Yes.
Good. Any? No. I just somebody furtively putting their hand up there. No. Nobody else. No more questions. Going. Gone. And so, thank you all very much. Thank you to all of the speakers. Thank you, Nicola. And have a very nice evening.